All right, Chapter 8 overview. So, there's two types of hypothesis tests that really matter from Chapter 8. So, one is a t-test, and the other is a one prop z-test. And you can find these if you do stat and then test, right? So, stat, then go to the test menu. You can see option 2 is t-test, option 5 is a one prop z-test. Okay, so that's where they live. Um, now, what's happening here? Let me come back to these assumptions after we do some example problems. But when we do these example problems, I want you to go through the steps of a hypothesis test rather than just do stat and then test. And so I'm going to make this a homework. And so I'll have you turn in your work online, and I want to see that you've done all these steps. Um, okay, so let's jump into the first problem. All right, for adults in a certain state, the historical rate of receiving a flu vaccine is 48%. A public health campaign was introduced to increase vaccine rates. In a recent study, 220 adults were randomly selected, and 121 reported receiving a flu vaccine this year. Fine. At the 5% significance level, do the data provide sufficient evidence to conclude, okay, to conclude what? To conclude that the proportion of adults, oh look, proportion of adults receiving the flu vaccine has increased. Okay, fine. So, I realize we didn't talk much about one prop z-test in class, but it's this should all feel the same, truly. Uh, t-test, one prop z-test. It'll just be, the problem directs us to the correct test. So in this case, we see we're talking about the proportion of the adults. Here we have a proportion of the people who got the flu vaccine out of, did it say out of? No, they don't. Okay, fine. Out of the 220, 121, right? This is another proportion. We see proportions all over the place in this problem. And so the whole reason why we want to select the one prob z test, the whole reason why knowing it's a proportion matters is because when we compute the test statistic, we know how it's distributed. We know the probability of getting what we got if the null hypothesis was true. So let's walk through this. What is the null hypothesis? So first off, let's just reread the part that starts with at the 5% significance level. Really, let's just jump to evidence to conclude. Okay. Whatever follows the phrase evidence to conclude, it's talking about your alternative hypothesis. So our alternative hypothesis is that the proportion of adults receiving the flu vaccine has increased. So H1, our alternative hypothesis, is that the proportion of adults receiving the flu vaccine has increased compared to what? Compared to our historical average, 0.48. So what's the null hypothesis? It's that it has not increased. The proportion of adults is 0.48. It's the same as it used to be. Okay. So if the proportion of adults was 0.48, if it hasn't changed, it's possible you just happen to ask where a lot of people got the vaccine. And so let's actually, what is our p hat, our sample proportion? Okay. Our sample proportion is 121 divided by 220. And if you put that in the calculator, you'll get 0.55. Okay. Look, it's possible we thought we did a random sample, and by random chance, we sampled a lot of people who got vaccines, right? Totally believable. Okay. So what are the chances of that actually happening? If if this is the true uh, population, I should do a subscript 0, even though um, I'm sort of mixing the notation that's on the calculator and the notation that I used here compared to the notation that we tend to use in class. Um, but okay, so if the true population proportion was 0.48, what's the probability that on a random chance our sample got 0.55? Well, that's determined by the test statistic because what's happening when we convert all this data to a test statistic, we're actually converting it to where we know the distribution. And so this test statistic, it's labeled with a Z, and that's why the name has a Z in the one prob Z test. What's happening is when you do this computation, the result lives on a standard normal. So let's do this computation. Uh, so it's p hat, okay, so that's 0.55 minus 0.48. So that's P sub 0. That formatting didn't work. I should fix that up. I'll do it later. Um, and P sub 0 is 0.48. Okay, divided by the square root of. And so over here, I need to do 0.48 1 minus 0.48, which is 0.52, 0.52, divided by n, which is 220. All that goes in the square root. So, okay, I have 0.48, and then I just suppose I'll just do 0.48, even though that's the same as 0.52, divided by 220. And so all of that goes underneath the square root. There we go. So this is 0.03368. Good enough. Okay, and so let me get rid of the square root because we already did it. We have 0.03368. And up top here, that's a 0.07. So I have 0.07 divided by the thing we got above, and that's 2.07819, blah, blah, blah. Okay. So here's our test statistic. All right, I want us to compute the p-value that is consistent with our alternative hypothesis and draw a picture. Okay, so what's happening is we have a z-score because this value here, if you go out and you take a random sample of 220 people and you see how many of them got vaccinated, that proportion, okay, you then sort of adjust and you divide by a standard error. That result that you get will be on a standard normal curve. So I can draw a standard normal curve. So it looks like a normal distribution, but I know the peak is at 0 because it's a standard normal. So it has mean 0 and standard deviation 1. I know that this distance here is 1. Okay. And my z-score is 2.07. So I'm going to double this distance to get me about here. So here's 2. And in fact, my value is 2.07. So maybe I'm right there. 2.07, whatever. Okay. And now, when I say compute the p-value consistent with your alternative hypothesis, well, the alternative hypothesis is that we should have been even further away. Or, I don't know. We expect p to be bigger than 0.48. So the probability of getting an observation that's bigger than what we got is our p-value. Okay. And the reason I say consistent is because if this was flipped, then we'd have to shade. Let me do this, I guess. We'd go from our observation and we go left. Okay. We'd have a big probability in that case. If it was differs, if this just said not equal to, then what matters is the distance to 0. So this distance is 2.078. I have to go an equal and opposite distance over here to negative 2.078. And then the p-value that I care about is all the stuff further away in absolute value. So it can be to that side, it can be to this side, but it'll be sort of symmetric and equally as far away from 0. Okay, we'll see that on the next problem. Okay, so part D, I want to compute the p-value consistent with the alternative hypothesis. This consistent with the alternative, that's letting me know it's this area that I need to compute. That area is my p-value. And draw pictures, that's what I've done here. Okay, now to compute the p-value, you do second vars normal CDF, so let's do that. So second vars normal CDF. What's our lower bound? It's 2.078. What's our upper bound? It doesn't exist, put in a big number. Mean is 0. Standard deviation is 1 because this is a normal 0, 1. That's where z-scores live. So what's the p-value that we get? We get 0.01885. I'm just going to stop there. I'm lazy. Okay. We'll skip this for a moment. I want to focus on F. So use the appropriate test on your calculator. So this is where I'm talking about we can do stat test now. And select draw instead of calculate. So the appropriate test, if we do stat, go to tests, this is a one prop z test. These have proportions floating around all over the place. Our test statistic has a z in the name. Our test statistic has a z in the name. Okay. And I already have this filled out. But what was our null hypothesis? Our null hypothesis is that the proportion is 0.48. Okay. How many people got the vaccine? What's our numerator? It's 121. What's our sample size, aka the denominator? It's 220. What is our alternative hypothesis? It's that more people got the vaccine because we're trying to increase vaccine rates. We did this health campaign, all that stuff. Okay. I'm not going to hit calculate, I'm going to hit draw. And what do you know? We get a picture that looks just like this, right? It's a bump, it's centered at 0. A little bit to the right of 2 is where our shading starts. And you can see on the bottom left of the calculator screen, it says z is equal to 2.078. You can see on the bottom center of the calculator screen, it says the p-value is 0.0188. Okay. So these steps, like we input this in the calculator, and the calculator does this stuff. Okay. The whole reason we have to select the correct test on the calculator, it's the same as you having to select the correct distribution over here. Okay. It's because the calculator needs to know what curve we're trying to get this area under. Okay. It also needs to know, am I shading to the right? Am I shading to the left? Am I doing two-tail? And so that's why we have to teach the calculator all these things. Okay. So, all right, with all of that in mind, let's do the skipped part, part E. So we need to state the conclusion. Okay, now look, there's a conclusion. If we go back to the problem, let me clear out some of this junk. Okay. To conclude, what's the conclusion? So that the proportion of adults receiving flu vaccine has increased. Can we conclude that? Okay, well, what does it mean to conclude it? So we have this alpha value of 0.05. It's a 5% significance level. And how does alpha compare to p? We can see, oh, p is less than alpha. Okay, and in fact, it's also true it's less or equal to alpha. And in this setting, when what we observe the probability of what we observe, or something more extreme, which is p, is less than our threshold, that's when we say, aha, there is sufficient evidence to reject the null hypothesis. We're going to reject that. And we're going to say there's sufficient evidence to support the alternative hypothesis. But what's the alternative hypothesis? It's what follows the conclude that. So it's this whole, the proportion of adults receiving the flu vaccine is increased. Okay. Ugh. How does the conclusion look? This looks like this phrase here. Okay. So at the 5% significance level, there is sufficient evidence. Why are you not sliding? There we go. Sufficient evidence to conclude that. And then I got lazy and I said, blah, blah, blah. Okay. Uh, the problem will tell you what you need to conclude. To conclude that, the proportion of adults receiving the flu vaccine is increased. I can copy and paste that. That is the best way to turn it into a sentence. Um, the proportion of adults receiving, before you accept after C, receiving, I don't know, the flu vaccine has increased. Okay, even I get lazy doing this. It's technically correct. You could be extra lazy and you can say to conclude that P is bigger than 0.48 because this is the alternative hypothesis written in math symbols. But if you want to write it in words, it's this, right? The proportion has increased. Increased compared to what? Increased to the old proportion, which is 0.48. Here we have P bigger than 0.48. Okay. All right. Cool. Let's do another. All right. International Automotive Report. Let me actually quit this out. Second quit and clear. Great. A National Automotive Report states that the mean fuel economy for a certain model of sedan is 31 miles per gallon. A random sample of 49 of these sedans. Oh, I never talked about the assumptions. Sorry, let's go back here. And I'm going to say that, look, in this problem, the one prop z-test problem, behind the scenes, all of these things are going to be true. Okay, so let's sort of walk through and see how they all show up. So do we have a simple random sample? Yes. So we randomly selected these adults that participated in this survey. The 220 adults were randomly selected. Is the population at least 20 times as big as the sample? So in this case, we're talking about adults in a certain state. That's our population. And look, 220, I was doing a calculator, 220 times 20 is 4,400. Every state has at least 4,400 people in it. Okay. So is the population, adults in a certain state, at least 20 times as large as the sample? Yes. Okay. So that's satisfied. Are individuals in the population divided into two groups? Yes. Those who got the vaccine and those who didn't. Okay. That's how we get a proportion. Okay, and then the most mathy one. So we need this number and this number to both be at least 10. What are these numbers? Okay, well, n, that's our sample size. P0, that was our initial, our old data for the proportion, so 0.48. But look, 0.48, that's about 1/2. It's about zero point 0.5. So if I multiply those two numbers, n times P0, what you get is about 100, right? Because it's 220 times about a half. And so yes, that is at least 10. And what's this one? Well, look, 1 minus P0, that's 1 minus 0.48. That's just what you have to add to get to 1. That's 0.52. And if I multiply 0.52 with 220, I'll also still get about 100. So yes, both of these numbers are at least 10. Okay. So anyway, uh, the fact that all of this is true is what lets us say, oh, we know how our observations should be distributed if you assume the null hypothesis, if you assume P is equal to 0.48. Okay. And so that's what lets us compute these probabilities and all these things. The assumptions for a t-test, much, much smaller. We need a simple random sample, and the sample size is at least 30, or the population is approximately normally distributed. So let's go look at problem 2. Look, a random sample of 49. That checks both boxes. It's random. The sample is at least 30. We're good to go. Okay, so this is screaming t-test. But let's continue. Let's see that it's a t-test. Uh, all right, so we do this sample, and in one state, fine, had a mean fuel efficiency. Okay, so this is a sample, and in the sample, there was a mean. So we have an X bar now. It's 32.4. In the sample, there is a standard deviation, S. It's 4.9. Okay. At the 5% significance level, do the data provide sufficient evidence to conclude that? Okay, so everything that follows is now H1. It's now the alternative hypothesis. The mean fuel efficiency in this state differs from 31. So the mean fuel efficiency differs from 31. That is the alternative hypothesis. Okay, so what does the null hypothesis have to be? It's that mu is 31. No, it does not differ. Okay. All right, so if in fact mu was 31, if that is true, it's possible that when we sample these 49 cars, we just got a couple of Priuses, man, and it just drove up this sample average. That's very possible. So we need to compute a test statistic in order to get a sense of how far away are we from the average. Okay, so my 32.4 minus my 31, that's the numerator, divided by S, which is 4.9, divided by the square root of our sample size, which is 49. Okay, fine. So what is this? This is 1.4 divided by 4.9 divided by 7. And what is this? This is 1.4. And this is like a 49 over 7, so you'll get a 7, but you have to move over a decimal. It's a 0.7. And what is that? It's 2. Okay. So we have a test statistic of 2, and the name of this test statistic is T because uh, this quantity follows a T distribution. Okay. The last one followed a standard normal distribution, and its name is Z. Okay. All right, so I want us to draw a picture again. Okay. And the good news is T distributions, they look like normal distributions. They look like standard normals. So you can draw the exact same picture. It's still centered at 0. And this is roughly 1. Okay. And so go that same distance again. We're out here, we're at 2. Okay, now, uh, consistent with your alternative hypothesis, to differ from 31, so that means this quantity here differs from 31, right? 31 is mu. So to differ from 31, and so we're going to change this X bar. It's going to differ from 31, but you want to do it in a way where you are at least a test statistic of 2 um, in absolute value. And what I'm trying to say is, if we were to sample some other cars and maybe instead of a bunch of Priusi, no one knows, we got a bunch of sedans that were less fuel efficient. I'm blanking on what that might be. I don't know. Um, but they end up being out here. And what type of number would that be? That'd be something like 29.6 would get us the same type of 29.6. That's the same distance from 31 as 31.4, right? So I add 1.4 Here I subtract 1.4. Um, so we'd be differing by the same amount. And our alternative hypothesis is just carrying whether or not we differ. Okay. The p-value is that you differ by at least that much, possibly more. So to differ by at least 2, I might be more than 2, I might be further than -2. It's that area. Okay. So this is the type of picture that we get when we have a differ type of alternative hypothesis. Okay. All right, let's compute the p-value now. So this is something we never had to do in this class, but to compute a probability from a t-distribution, you have to use a t-CDF. So I do second vars t-CDF. Okay, now this distribution is also symmetric. So this area here, it's the same as this area here. So the total area, which is our p-value, is 2 times this thing or this thing, whichever, whether you want to do the left or the right. I'm going to do the left because the calculator's default is to compute area to the left. So my lower bound, it doesn't exist. It's minus infinity. It just keeps going. My upper bound is this -2, -2. Degrees of freedom. Degrees of freedom is 1 less than your sample size. We have a sample size of 49. So 49 minus 1 is 48. Okay. Paste, enter. So this area here is 0.025587, blah, blah, blah. Who cares? Okay. I have to multiply it by 2 to get the actual p-value, right? Because I need to get this area plus this area. Okay, and they're the same area. So I multiply by 2. So my p-value is 0.05117. Okay, fine. Aha. So state the conclusion. So we need to compare p with alpha. All right. Our alpha value, we have a 5% significance level. So alpha is 0.05. Our p-value is 0.05117. So p is bigger than alpha. So this is when we do not reject. We fail to reject. Fail to reject H naught. Okay. As a recap, reminder, p less or equal to alpha, that means you reject H naught. And so to not reject means this is flipped, right? This double arrow means if and only if. So the top happens, the bottom happens, the bottom happens, top happens, whatever. Okay. So, if I were to state the conclusion, remember I have this template here for what it means to state a conclusion. At the 5% significant level, there is not sufficient evidence to conclude that. And the problem will always say, to conclude that, okay, here's what we're supposed to, right? So, um, at the 5% significance level, there is not sufficient evidence to conclude that. And I could copy and paste the mean fuel efficiency in this state differs from 31. So there's not sufficient evidence to conclude that the mean fuel efficiency in this state differs from 31. Oh, what a mouthful. Ultimately, that is in words what the alternative hypothesis is. It's hard to see, it's in yellow. The alternative hypothesis is that mu differs from 31. So there's not sufficient evidence to conclude that mu differs from 31. Okay, I'll also accept that. Okay. But, I just want you to know, it's not a coincidence that the phrasing of conclusion and it's designed to be very, follow your nose type thing. That's how hypothesis test works. Let's use the calculator now. So for the calculator, we're going to go stat, go over to tests. This is a t-test. We're going to enter statistics. The null hypothesis is that the mean is 31. The sample that we had was 32.4. Sample standard deviation, sample size, alternative hypothesis there. Go down to draw, and we get this exact picture. It's this, bell-shaped looking curve. And we can see on the bottom left of that calculator screen, t equals 2. So that's our test statistic. We can see in the bottom center, the p-value, they rounded. They have 0.0512, right? If We got 0.05117, so that just rounded up. And we can see that their little area, it agrees with what we drew, right? It's at least 2 units from zero. Okay. Okay. So cool. I've now done those first two. You have 6 for practice. And so I want you to go through those for your homework. Um, Here's the other type of question that we might have. So I'm just trying to show us things different from Alex. And so part of why I want you to do that for your homework is because when we start quizzing you on p-value, you have a better understanding of what p-value is. Okay, so the p-value is this area, and the area that you care about depends on your alternative hypothesis. So here, this is right-tailed. Okay, so in its little picture, it's only on the right that it cares about. Here, this is two-tailed, so that's like what's on the calculator screen right now. Left-tailed, right? It only cares about what's going further left. Okay. And so let's take a peek at, I don't know, I'll just do problem 3. Okay. All right. So there's some hypothesis. Okay. Apparently it's that some proportion is 20%. And there's an alternative hypothesis. No, no, no. The proportion should be less than 20%. So we go and we do a random sample and we find a test statistic of negative 1.28. Okay, so right here is minus 1.28. So then the p-value is this area here. It's 0.1003. Okay. It's the area to the left because this is a left alternative hypothesis. Okay. Assuming the null hypothesis is true. So the reason for that line is it's what fixed this curve. Every time your calculator, look, how can we subtract a mu if we don't know a mu? So in our computation, we subtract 31. What we're doing in that computation is assuming 31 is mu. If 31 is mu, what's the probability that you are this far away from mu? Which means you could also go to the left, right? That's what a p-value is. Or over here, assuming the population proportion that get the vaccine is 0.48. That's how we computed this. That's how we compute this z-score here, right? And so then you can compute the probability. What's the probability that you just happen to get a sample of people with high vaccination rates? You happen to get people out here on the right. Okay. So when it says, assuming the null hypothesis is true, that's what allows us to draw this curve. That's what allows us to get this test statistic. Okay. If that confuses you, you can legitimately just delete it and just skip to this following part of the question. What is the probability of obtaining a new test statistic smaller than the one already observed? Now, smaller in a math context um, means more left. Okay, so what's the probability that you land in this region? And the answer is your p-value. The answer is 0.1003. That's what a p-value is telling you. Okay. All of these questions are designed to reiterate the definition of a p-value. The p-value is the probability of obtaining a new test statistic that is more extreme than what you've already observed. So what does it mean to be more extreme? Well, on a left tail case, more extreme means more to the left. On a right-tailed case, more extreme means more to the right. On a two-tailed case, more extreme means as far away from zero as where you currently are, right? So, okay. This is, if you are kind of getting that, this is why, so now I'm going to come back up here to my remark. It can be a confusing remark because I'm trying to capture all of this in like a catchy phrase. So what's a p-value? It's the probability of observing your test statistic or something more extreme, okay? What does more extreme mean? It could mean larger. It could mean as far away from zero or more. It could mean smaller, aka more to the left. What more extreme means depends on your alternative hypothesis, as determined by your alternative hypothesis. Is it more to the right? Is it more to the left? Is it just farther away from zero? Assuming the null hypothesis, again, you could just kind of cross that out. It's just saying that we have this curve, okay? That's what a p-value is. So all these phrases are doing. Now, I could have continued this and tried to trick you even more. So let me show you what that type of question would look like. So since we've already began this question, okay, uh, pretend for a moment that instead it said, what is the probability of observing new test statistic larger? It doesn't say smaller. So now, same picture, we're over here, minus 1.28. This p-value is this area. It's the probability that you move left. So now this problem is saying, what's the probability you move right? Ah, well, the total area under the curve is 1. So 1 minus 0.1003 is 0.8997. It seems reasonable. Okay. Then that would be the answer. Okay. Uh, so it's very likely. Look, if the true proportion is 20% and you got something less than 20%, that's not very common because the true proportion is 20%, assuming the null hypothesis is true. Okay? So this is not common. So it would be a bigger p-value to get a larger thing than what you got. Anyway, if that doesn't make sense, you can comment, you can talk to me during class, you can email me. Let me know. Do you see what I'm saying here? How we could sort of tweak this? So, all right, work through these problems, please. Error types. Okay, so let's just do a quick little review of the error stuff. So the null hypothesis, okay, it might be true and it might be false. Okay. That's something we don't know. This is just, some, I don't know, God-given thing. We don't know it, but it either is true or false. Eh. Um, what we know is what our data tells us. Okay. So we can go out and collect samples, and based on our data, we might reject the null hypothesis, or we might not reject the null hypothesis. If we reject something that is true, we made a mistake. We made an error. That's called a type 1 error. If we reject something that's false, we did a correct decision. Okay. If we do not reject something that's true, we did a correct decision. And if we do not reject something that is false, we made a type 2 error. Okay. You should have this on your exam reference sheets unless you are fully confident that you memorized it. But these are error types. Okay, so a manufacturer claims that the mean lifetime of some LED bulb is 50 months. Okay, so their claim uh, is this. A student takes a sample of 40 light bulbs and performs a test at the 5% significance level. Fine. The test results are blah. Okay. One-sided p-value. So look, so based on this p-value, p is less than alpha, they are rejecting the manufacturer's claim. So they live here. Okay. They're either going to do a type 1 error or a correct choice. Okay. Suppose the true mean lifetime really is 50. So we're supposed to be here. What type of error occurred? A type 1 error. Okay. The answer to this is a type 1 error. Did an error occur? Yes, type 1. All right. How many of these do we have? We only have 3. All right. So I'll leave these other 2 for you all to do. Okay. So, more practice with these. For these, for group, I just want you to just use your test on your calculator. So this is a stat test type of thing, and just use the correct test. Just more practice with, can you suss out when is it a t-test, when is it a prop 1 z-test? Um, uh, a good giveaway, okay, for t-test. They'll talk about some standard deviation. Okay, you don't need a standard deviation for a 1 prop z-test. So if you read this problem, there's no mention of standard deviation because the standard deviation is this square root of p1 minus p. So the fact that in our hypothesis tests, we're always going to have this H0, which in this case says that p, okay, has changed from, okay, so the null hypothesis is that 60% of people something here don't care. Okay. Uh, So then you can just straight up compute sigma. It's 0.62 times 1 minus 0.62, which is what you add to get 1, which is 0.38 square root. Okay, it's this computation. So they don't need to tell you. It's implicit. Okay. But anyway, so this is going to be a 1 prop C, whereas this is going to be a T, right? And so if it has standard deviation, t-test, no standard deviation's got props. Okay, so you can go through those, get more uh, just simple tests, but okay, that's it. That's what I want to talk about for the chapter 8 overview. Um,